All right, welcome to 6.7. 6.7 is what this entire chapter has been working towards. The reason we want to model things with exponential functions. But in order to talk about exponential functions, we have to use logarithms. Logarithms are inverses. And that lets us solve exponential equations. So when we set things up with exponentials, model real life stuff with exponential functions, we have all the tools to do that. And of course, to do logarithms, we needed to talk about inverses. We needed to talk about function compositions to talk about inverses, and it all ties together for us to be able to do something like this. So without further ado, let's begin. We're going to start by talking about radioactive decay. Bunch of different applications here, and I kind of want to do like 10 hours of videos on this, but that might be a little bit much, but there's some really cool stuff out there. And we're going to talk about a couple of them. Example 1. Let's look at the percent P of T of carbon-14, which is sometimes abbreviated as C with a 14 as kind of like a superscript before it. Remaining in something after T years can be modeled by the following table. So I'm going to give you a table of some T values in years and some percentages. So originally, right now, what percent do we have remaining? Well, let's just say we have 100%. Okay. Then after 5,730 years, I'm going to tell you that we now have 50%. And after another 5,730 years, so that's going to be 11,460, the problem is telling us that we now have 25%. After another 5,730 years, this is 17,190 years in the future. 12.5% is remaining. This is radioactive decay, okay? And I'm not much of a chemist, so I won't give a really detailed example for why this works or how this carbon-14 is decaying, but it is pretty interesting if you want to read a little bit about it. But the fact of the matter is that this decay rate is constant. So we lose half of it in the first 5,730 years. Right? We're starting with an entire piece of the pie. Then after 5,730 years, we only have this. After 5,730 years, this is how much is left. But it keeps decaying. After another 5,730 years, we lose half more of it. After that second chunk, now we only have a quarter of what we started with, right? And then again, we lose another half. And now we have an eighth of what we started with. And every half-life, every duration of 5,730 years, we're going to lose half more of what we have remaining. Okay? But I haven't asked any questions yet. I'm getting a little ahead of myself. Letter A. Estimate what percent is left after 22,920 years. So hopefully that has to do with another half-life. Another set of 5,730 years. I haven't introduced the term half-life yet, but I'm already using it. Okay. Well, notice, that's part of our solution, right? Notice that 22,920 is just the last data point plus 5730. So we're losing half every 5,730 years. So we're just going to lose another half. So we're going to guess, well, what's half of 12.5? You can use a calculator. Our answer is going to be this is what percent is remaining. All of these P of T's are written as a percent. What percent? 6.25%. Part B. There we go. Part B says the half-life. Hey, there it is. The half-life of an exponentially decaying quantity it's the time required for half the quantity to decay. That's what the definition of half-life is. How long? Half-life is a time. And specifically, how long does it take half of that material to decay? I literally just saw half-life mentioned in an article the other day. It's saying that our concern for for global events has a half-life, which means our concern for global events is exponentially decaying, which is sad, but it is true. So half-life is also sometimes used, not in math, but it has the same meaning. Okay, so the question is, what is the half-life of carbon-14? Again, carbon-14 is abbreviated like this. Well, half-life is just the time required for half of the stuff to decay. And notice that our stuff is decaying by half every 5,730 years. All right, so every 5,730 years, decays by half. Another 5,730 years, decays by half again. And so on and so on. Okay? Maybe write it like this. 1/2 gets multiplied by a half again. So this right here, the distance between these two things is our half-life. 5,730 years. If I got a chunk of carbon-14, then if I sit around for a while, holding a chunk of carbon-14, sit around for 5,730 years, well, now I only have half of it. Okay, or half of it is carbon-14 still. I don't remember what it decays into. Again, I'm not really a chemist. Let's do part C. Use this information to find a formula A of T equals A naught e to the KT. For the percent left, after T years. We want to model this. Let's model this percent with an equation. We'll model it with an exponential equation. And we're going to do this by plugging in some points. Okay? So that A naught, that coefficient, is usually going to be the starting value. A naught, that's what's known as the starting value. When T is equal to 0. Because when T is equal to 0, what happens? When T equals 0, this becomes e to the 0, which is 1. That's why that A naught is that starting value, because everything else goes away. Okay, let's look at this. All right, K is going to be our growth or decay rate. And oftentimes we're going to have to find. And it can be a little messy. Let's do that. Let's try to fill in the blanks. A naught e to the KT. Well, let's plug in some points and try to solve for some of these letters. So when T equals 0, what percent do we have? Plug in some points to figure these out. When t equals 0, our percent is 100%. We have 100%. That's going to be our a of t, or a of 0. Plug in 0, we should get 100%. Plug in t, plug in our value of a, and let's figure out what this constant is. This simplifies to 100 equals a naught, or a sub 0, times e to the 0. It doesn't matter what k is. K times 0 is still going to be 0. Well, this is 100 equals a naught times 1. Oh, a naught is 100. I said a naught is usually that starting value. That's why. So our function is 100 times e to the kt. But now we need to find k. And this is where things get a little trickier. We're going to need another point. You can choose any of these points. I'm going to choose the one that's the simplest. When t is 5730, p is 50%. So t is 5730 years. We have now 50%. Or in other words, you could say that a, the amount remaining, the percent remaining after 5,730 years is 50%. Now plug in these ones and let's solve for our k. We're going to have to solve. Oh, I don't want to get ahead of myself. 50 is equal to 100 times e to the k times t. And our t here is 5730. This is an exponential equation that we have to solve. Well, we've been solving exponential equations for maybe a week or so now. We can solve this. How do we solve this? We have to isolate the exponential function. So to do that, we're going to divide both sides by 100. Get that exponential function by itself. 50 over 100 is 1/2. That's not a coincidence. And that's going to equal just e to the 5730k. Well, once the exponential function is isolated, now we can take the logarithm of both sides. And I'm going to choose the natural log here because that's the inverse of e to the x. So the left-hand side, we get the natural log of 1/2. And the right-hand side, these are inverse functions. They cancel each other out. We're just left with 5730k. Properties of logarithms coming back. Now all that's left is dividing by 5730, and that finds us our value of k. Right? K is just the natural log of 1/2 over 5730, and we can approximate that with a calculator. A lot of times we actually write it like this. Why is that? How are these the same thing? Remember, if I have a number being multiplied by a logarithm, that number is the same thing as an exponent inside. What's 2 to the negative first power? That's 1/2. So these are the same things, just using properties of exponents and logarithms. So let's type this into a calculator. Oh, I don't have my calculator ready. All right, well, I'll type it in the calculator on a different monitor. You just have to trust that I'm doing it correctly. The natural log of 1/2 divided by 5730 is negative 0. Oh, it went away. A lot of zeros. 0.000121. We should include a couple more digits if we want to be even more exact, but roughly, this is about what it equals. Why do we need k? It's been a while. Because we're looking for this formula. And this formula has two parameters, a naught and k. And we needed both. And now we have them. A of t is equal to a naught, which we found was 100, times e to the k, which we found was about 0.000121, times T. This is our formula for part C. All right, we can use some more stuff with this. In part D, say what percent is left after 7,000 years? And we should have an expectation here. We can look at the data and have an expectation. How much is after 7,000 years? Well, 7,000 years is somewhere in here. Maybe closer to, if maybe 40 something percent. I don't know. It's going to be somewhere between 25 and 50%. And we can get a good guess with this function. It's just finding, all right, what percent is left after 7,000 years? Plug in 7,000 years into our formula and see what we get. Be very careful with your parentheses here. All right. Here, I think I can show it like this, even though I didn't prepare this. We're going to look at 100 times e raised to the negative 0.000121 times t, which is 7,000. I believe I typed things incorrectly. Yep, typed in correctly, not typed incorrectly. And we're going to get the amount left is about 42.87. This percent is what's left over, which is we guessed about 40 something percent. Well, I guessed about 47%. I don't know what your guess was. Hopefully you were guessing at home. All right. And that's pretty much what we could do. We could also do another part, estimating when 30% was left. Should be close to 2 half-lives. But we're going to move on, do 2 more different kinds of problems before this video ends. This is the biggest video, probably. I want to make sure to show a lot of different types of problems connecting these concepts. Let's do example 2. A substance, so we're not talking about carbon-14 anymore. Some other substance has a half-life of 5.2 minutes. It decays much more quickly than carbon-14. Carbon-14 took over 5,000 years for half of it to decay. Here, this substance, half of it's decaying every 5 minutes. Okay, so it's decaying pretty quickly. I mean, relative to carbon-14 at least. All right, if the initial amount is 112.5 grams, part A wants to know how many half-lives, you'd use a V here, right? How many half-lives have passed or will have passed before 7.03125 grams remain? So this just wants you to be able to make a conceptual connection with what a half-life is. Right? We start, right, 0 half-lives. We have 112.5 grams. After 1 half-life, how much do we have? Half remaining. After a half-life, we now have half of what we used to have. That's the whole idea of half-life. We just divide this number by 2. Or multiply by a half. All right, that's going to be, I shouldn't do this in my head. 112.5 divided by 2. 56.25. After another half-life, we now have half of that. 28.125. After another half-life, we have half of that. 14.0625. After another half-life, we cut that in half. 7.03125. And these are all in grams. Every half-life the amount remaining gets cut in half. So the question is, how many half-lives will have passed before that much remains? And the answer is 4. It takes 4 half-lives for this to decay so far. That's our answer. And part B asks a similar question. How much time is that? How much time is 4 half-lives? Well, 1 half-life we said was 5.2 minutes. So what's 4 half-lives? It's just 4 times 5.2. That's 20.8 minutes. And that's a perfectly decent answer, full credit. What's 0.8 of a minute though? Right, 20.8 minutes. That's 20 minutes plus 0.8 of a minute. What's 0.8 of a minute? That's 0.8 times 60 seconds. So it'd be a little bit better to write our answer like that. 0.8 times 60 seconds is 48 seconds. So the best answer, again, this is okay. The best answer would be to say 20 minutes, 48 seconds. All right. That's how we solve this problem. Let's do one more, just to give you a little bit more exposure to different kinds of problems. And then the next video, we're going to talk about logistic growth, which is useful for populations and diseases. All right. Example 3. A doctor is prescribing 110 milligrams of a drug that decays by about 35% every hour. So this touches a little bit with the last video of this section. Kind of connects a couple things together. Model this, not with E, but for part A, model this with the equation A equals little a times b to the x. Let's connect things back to 6.1. Right? Yeah, sometimes we have e to the x, but sometimes we have b to the x. The base doesn't always have to equal e. Remember, b was that growth or decay factor, so if we were doubling, right? We were doubling, b would equal 2. We were tripling, right? B would equal 3. If we were growing by 20%, B would equal 1.2. We talked a lot about this in 6.1. But now we're decaying by 35%. What's B going to be? And also remember that A is our starting value. Think back to 6.1. So this is going to give us that A equals our starting value times B to the X, where X is in hours. And A is in milligrams. So the question is, what's our B? Well, if we grew by 35%, then it'd be 1.35. Decaying by 30%, it's going to be 1 minus 35%, 0.65. Every hour, if we're losing 35%, that means every hour we have 65%. Right? If we're losing 35%, that means we have 65%. And you can't simplify this anymore. That's our answer to part A. Lose 35% means we retain 65%, and that's how we find our B value. Let's do part B. Model this with our new formula that we used in the last two examples, or the first example. A of t equals A naught e to the kt. Well, so the A naught part is just going to be the same, right? These are both the initial value. A naught still 110. That part's not too bad. But if I want base E, how do I do that? There's a trick that we talk more about in the last video here. But notice, right, 0.65 equals e to the natural log of 0.65. This is true, right? It's true because they're inverse functions. So if I want an e, I can just make an e this way. These are the exact same thing. So what I'm going to do is rewrite 0.65. And there's still an x as the exponent. I'm just going to rewrite 0.65 like I did in the yellow here. It's e to the natural log of 0.65. And now we've almost done what we've been asked. It's almost in this formula. Oh, I said we should have an x, but this problem is telling us to have a t as our variable. How do we simplify an exponential like this? An exponent raised to another exponent. We're just going to multiply those exponents. We're going to get a of t equals 100 times e to the ln 0.65 times t. These two boxed equations are identical. These two boxed equations mean the exact same thing. And our k is just the natural log of 0.65. So these two things are the same, just different forms. Sometimes working with e is better. It's kind of like a standard. We can be standardized that way. And then sometimes it can be a little bit easier conceptually to use the b value instead of e, especially if we're like doubling or doing something like this. This is how you convert between these two things. We do this a little bit more in the last video of this section. Part C. What is the half-life of this drug? Well, check back to our notes. What the heck does half-life even mean? The half-life of an exponentially decaying quantity is the time required for half the quantity to decay. So in our case, it's going to be the time until half decays. Well, if we started with 110, right? Started with 110 milligrams. How long until half is left? That's our half-life. Half-life is how long does it take until half decays? If we started with 110 milligrams, we find the half-life by figuring out how long it takes until 55 is left. And you can use either equation to solve this. You can use the first equation or the second equation. No problem. The second equation is more common though, but you can use either. So in other words, when is A of t equal to 55 milligrams? So you just plug that in. 55 milligrams is 110 e to the natural log of 0.65 times t. Solve for t. Exponential equation. Get that exponential function by itself. And again, it's 6.6 all over again. We had a whole section on that, so I'm going to go through it kind of quickly. Divide by 110. This will always equal 1/2 if it's the half-life. That's a juicy little morsel that I'm not going to spend too much time on, but it will always be a half, right here, no matter what we started with, if we are solving for the half-life, equals e to the ln of 0.65 times t. Now be very careful. We cannot cancel like this because there's also a t here. All right. So we still have to take the natural log of both sides. That's going to give us the natural log of 1/2 equals, now they cancel, the natural log of 0.65 times t. And now we divide by this natural log. And we're going to get that t is equal to the natural log of 1/2 or negative natural log of 2 divided by the natural log of 0.65. Type that into a calculator and we're going to be good to go. Natural log of 1/2 divided by the natural log of 0.65, about 1.6090. Or, what is our units? It's decaying by 35% every hour. Okay, so this is how many hours? About an hour and 40 minutes about. Again, this is an okay answer. Even better would be to say how much is 0.6 hours? Well, 0.6090 hours is this many minutes? About 37 minutes. That's the half-life. Half-life is also related to doubling time. You may see this word as well. I don't remember whether this pops up on the homework, but doubling time is another definition. And it's basically the same thing as half-life, but when things are growing. So if things are decaying, we talk about the half-life, how long it takes to half. Well, the doubling time is just the time it takes something to double. So if you have exponential growth, you might see this mentioned. All right, and that's everything. Got a nice, big, strong video to lead us in to 6.7. The other ones should be shorter, but there's a lot going on here with radioactive decay. Good luck, and please reach out if you have questions.